Hello, welcome back to the playlist of topics on regression models and statistical machine learning. I'm Hemakumar Kasala, and as part of this video, we learn additional statistical parameters that help in choosing the correct model among the available list of candidate models. In this part of the video, we learn about predicted R-square and understand its role in addition to R-square and adjusted R-square. We learn about Mallows Cp, a statistic that provide insight in finding if there is a bias introduced in the model as a result of missing important predictors in the model. And we learn additional statistical measures, namely AIC, BIC or SBC and APC, which help in choosing a model among the available alternatives that offer a balance between an overfit and an underfit model. Let's get into the video. Lecture 10. Multiple linear regression models, predicted R-square, Mallows Cp, AIC, BIC or SBC and APC. Before we get to understand the best subsets regression method, we need to understand a few more statistical parameters that provide more information on additional criteria for model evaluation. Predicted R-square, Mallows Cp, AIC's information criteria, in short called as AIC, Bayesian information criteria, in short called as BIC, also called as Schwartz Bayesian criteria or SBC, and Amanier's prediction criteria, APC. Let's get to learn them one by one. Of which we already encountered predicted R-square and Mallows Cp as part of our discussion on stepwise regression method, but deferred dwelling into the details. By definition, predicted R-square equals 1 minus predicted sum of squares divided by total sum of squares, where predicted sum of squares is arrived as follows. From a sample of size n, each time one observation at ith location is dropped and the regression equation is calculated. The difference between the predicted value of y at I denoted by yi hat and actual value of y at I, which is yi, is calculated as in yi minus yii hat. Please note the illustration uses a simple linear regression case just for the sake of ease in visualization. This procedure is repeated n times for every other observation in the sample, and yi minus yii hat is calculated for each value of I. Predicted SS then equals sigma I equals 1 to n yi minus yii hat the whole square. Note the difference between the predicted sum of squares and the residual sum of squares. Predicted sum of squares equal sigma I equal to 1 to n yi minus yii hat the whole square, and residual sum of squares equal sigma I equals 1 to n yi minus yi hat the whole square. Difference is primarily in the way the predicted value yi hat and yi hat are calculated. Lower the predicted sum of squares, higher is the predicted R-square, and higher is the model's predictive ability. Predicted R-square acts as a useful statistic to check if the model is overfitted. An overfitted model is a result of too many extraneous predictors making way into the model. Such a overfitted model fits every observation in the sample so well, as a result, the observation left out in each step while calculating the predicted R-square tends to fall away from the regression function, resulting in higher values of predicted sum of squares and eventually lower values of predicted R-square. Thus, predicted R-square helps judge the predictive ability of the model without requiring the available data to be split as train and validation data. A high R-square with low predicted R-square indicate a model that is perhaps overfitted. Predicted sum of squares and predicted R-square are sensitive to outliers. Larger the outliers are and or more number of outliers can potentially make predicted sum of squares even greater than the total sum of squares, which can result in negative values of predicted R square. In such a case, the predicted R square is limited to 0. While predicted R square checks the model for overfitting, checks are also needed to ensure the model is not underspecified. Underspecified models miss important predictors. Mallows Cp is a statistic that helps verify if a model is underspecified. Underspecified models, as a consequence of missing important predictors, results in biased coefficients. Biased coefficients results in biased predictions. Obviously, biased predictions are not preferred, and Mallows Cp estimates the size of the bias. The predicted response minus population's response mean given the predictor values at ith instance, which is given by yi hat minus yi bar, exhibits a variance that has two components. The first one being the variance in the predicted responses across samples due to sampling variability. The second one is the deviation between the estimated predicted response E of yi hat and the estimated value of the response variable E of yi, also denoted by yi bar, at that given instance of the predictor values. This difference, E of yi hat minus E of yi, is the bias, and it varies depending on the important predictors missed out in the model. The illustration of variance in predicted responses across samples due to sampling variability is easier using a simple linear regression case as against a multiple regression case, which is almost impossible. Variation in the regression functions across all possible random samples looks something like this. The variance in the predicted responses across samples for a given value of the predictor at ith instance can be seen as shown above. In the absence of a bias, the mean of the predicted responses calculated using the estimated regression function across samples should fall on the unknown population regression function line. However, when bias exists, which is often the case when important predictors are left out of the model, the mean of the predicted responses do not align with the population regression function and remain deviated from the population regression function like this or like this. Therefore, the total variance in yi hat minus yi bar is the sum of the variance due to sampling variability and the difference E of yi hat minus E of yi, which is due to bias. The total variance is not the same for every set of predictor values. Total variance at xx is different from that at xy. Variance in predicted responses introduced because of bias is large when important predictors are not included in the model and small when almost all of the important predictors are included in the model. Mallows Cp is a statistic that is used to judge the presence of the variance due to bias in the overall variance. That is, overall variance in the residuals. In other words, residual sum of squares SSR. Let's understand how Mallows Cp is calculated. As discussed, total variance in yi hat minus yi bar is the sum of the variance due to sampling variability denoted as sigma yi hat and variance due to bias denoted as bi. Total variance at ith observation xi is not the same as that at jth observation xj. Therefore, total variance at any one observation does not convey any useful information. And hence, total variance across all data points from a sample is considered. Normalized total variance denoted by gamma p equals 1 divided by sigma e square multiplied by sigma 1 to n sigma yi hat square plus sigma 1 to n estimated yi hat minus estimated yi the whole square. In the above formula for gamma p, sigma 1 to n sigma yi hat square is the sum of the variances due to sampling variability in predicted responses at each observation I across n observations in the sample. Sigma 1 to n estimated yi hat minus estimated yi whole square is the sum of the bias in predicted responses at each observation I. Sigma e square in the denominator in the above equation for gamma p is used to normalize the total variance. Sigma e square is the unknown population mean error sum of squares MSE with respect to the population regression expression. 1 divided by sigma e square multiplied by sigma 1 to n sigma yi hat square in the normalized total variance gamma p describe that part of the total sum of variances due to sampling variability in multiples of variance in the population error. 1 divided by sigma e square multiplied by sigma 1 to n estimated yi hat minus estimated yi the whole square in the normalized total variance gamma p describe the sum of the biases in the predicted responses in multiples of variance in the population error. When there is no bias, that is sigma 1 to n estimated yi hat minus estimated yi the whole square equals 0, it can be proved that normalized total variance gamma p equals 1 divided by sigma e square multiplied by sigma 1 to n sigma yi hat square plus 0 equals p, where p is the number of predictors plus 1, where 1 stands for the intercept. When there is no bias, gamma p equals p implies sum of the variances in the predicted responses due to sampling variability at all data points in the sample equals p multiplied by variance, which is sigma e square. Therefore, gamma p as defined in this equation is a good measure to check if the model is underspecified. A correct model is a one whose gamma p is the least, though the theoretical minimum is p, where p stands for the number of predictors included in the model plus 1. However, there is an issue in calculating gamma p. Sigma e square in gamma p is the error variance about the population regression function. Estimated yi in gamma p is the mean value provided by the population regression function at ith data point. Both are population parameters and hence unknown. Similarly, sigma yi hat square and estimated yi hat in gamma p are also not readily known. Therefore, we need to estimate gamma p since calculating the same is almost impossible. There comes the role for Mallows Cp. Mallows Cp is an estimate of the normalized total variance gamma p, which is computable. Mallows Cp is defined as follows. Mallows Cp denoted as Cp equals p plus MSRp minus MSR all multiplied by n minus p divided by MSR all, where p equals number of predictors plus 1. MSRp is the mean residual sum of squares when p minus 1 predictors are added to the model. MSR all is the mean residual sum of squares when all potential or qualifying predictors are added to the model, and n is the sample size. MSRp minus MSR all multiplied by n minus p divided by MSR all in Cp becomes 0 when there is no bias, much like 1 divided by sigma e square multiplied by sigma 1 to n estimated yi hat minus estimated yi the whole square in gamma p becomes 0 when there is no bias. That implies MSRP minus MSR all multiplied by n minus p divided by MSR all in Cp is an estimate of 1 divided by sigma e square multiplied by sigma 1 to n estimated yi hat minus estimated yi the whole square in gamma p. We saw that when there is no bias, normalized total variance gamma p, which equals 1 divided by sigma e square multiplied by sigma 1 to n sigma yi hat square plus sigma 1 to n estimated yi hat minus estimated yi the whole square equals p, where sigma 1 to n estimated yi hat minus estimated yi the whole square becomes 0. Similarly, when there is no bias, Mallows Cp, the estimate for gamma p, which equals p plus MSR p minus MSR all multiplied by n minus p divided by MSR all equals p, where MSR p minus MSR all multiplied by n minus p divided by MSR all becomes 0. The ratio MSRP minus MSR all multiplied by n minus p divided by MSR all in Cp is the residual sum of squares left unexplained because of the missing all minus p minus 1 predictors in the model, which is MSRP minus MSR all multiplied by n minus p in the numerator, expressed in multiples of variance in the residuals of the model with all predictors included in the model, which is MSR all in the denominator. 1 divided by sigma e square multiplied by sigma 1 to n estimated yi hat minus estimated yi the whole square in gamma p is the regression sum of squares SS reg left unexplained because of the missing all minus p minus 1 parameters in the model. Mallows Cp estimates 1 divided by sigma e square multiplied by sigma 1 to n estimated yi hat minus estimated yi the whole square in gamma p, which is the regression sum of squares SS reg left unexplained by the model because of the missing predictors, using MSRP minus MSR all multiplied by n minus p divided by MSR all, which is the residual sum of squares left unexplained by the model because of the missing predictors. Regression sum of squares SS reg left unexplained by the model is always the same as the residual sum of squares left unexplained by the model. This equality justifies the use of the estimate Mallows Cp in place of gamma p. When the mean residual sum of squares MSRP with p minus 1 predictors included in the model is almost equal to the mean residual sum of squares MSR all with all potential or qualifying predictors included in the model, Mallows Cp converges towards p, which is number of predictors included in the model plus 1. That concludes the model coefficients are free of any bias. Cp can be further simplified as p plus MSRP divided by MSR all multiplied by n minus p minus MSR all divided by MSR all multiplied by n minus p. Since MSRP multiplied by n minus p equals SSRP, which is the residual sum of squares when p minus 1 number of predictors are included in the model, Cp equals p plus SSRP divided by MSR all minus n minus p, which further can be rearranged as Cp equals SSRP divided by MSR all minus n minus 2p. When there is no bias, Mallows Cp tends towards the number of parameters p in the model, which is the number of predictors plus 1. In other words, Cp equals p. The best subsets method uses the Mallows Cp to choose the best model among the alternatives. Here is an example output of a best subsets method with 4 candidate predictors. We will discuss in detail on the best subsets method itself soon, But in this example, we just pay attention to the figures, namely the Mallows Cp value and the number of predictors used in each subset to come to a conclusion. Each row in the table represents a candidate model with certain number of predictors. There are in total 7 candidate models listed, and the first row is a model with one predictor x4 included. And the last row is a model with 4 predictors x1, x2, x3 and x4 included. The columns that we pay attention to for now are the wheres column, that is the number of predictors included in each subset, and the Mallows Cp column. We learned that the models with least bias produce a Mallows Cp that equals P, which equals wheres in the table below plus 1. The models or rows in the below table that qualifies the above criteria are rows 3, 5 and 6. Row 3 being the closest to satisfy the Mallows Cp criteria. In all these 3 cases, Mallows Cp is less than P. Cp less than P, which is wheres plus 1. Cp less than P represents no bias as much as Cp equals to P. Therefore, Cp less than or equal to P represents a no bias situation. Which one among the 3 models will be chosen for deployment is the question that we will understand as part of the best subsets method. As for now, we see this example to understand the placeholder for Mallows Cp in the statistical tables to judge the bias, if any, among the candidate models. That concludes our understanding of Mallows Cp. We will see how this is used in the model selection using the best subsets method soon. There are 3 additional statistical measures that help choose the best model among the candidate models. These are called as the information criteria statistics, namely Akai's information criteria AIC, Bayesian information criteria BIC, also called as Schwartz Bayesian criteria SBC, and Amelia's prediction criteria APC. AIC and BIC or SBC are the statistics that estimate the information loss, in other words the prediction errors in each of the candidate models. A model with least value of AIC or BIC is recommended as the model that provides the best fit among the rest, balancing between or avoiding an overfit and an underfit situation. The formulas to calculate the statistics are AIC equals the sample size n multiplied by natural logarithm of the residual sum of squares SSR minus n multiplied by natural logarithm of n plus 2 multiplied by number of predictors included in the model plus 1, which is P. BIC equals n multiplied by natural logarithm of SSR minus n multiplied by natural logarithm of n plus P multiplied by natural logarithm of n. As can be seen in the formulas, for a given sample size of n, larger the SSR, larger is AIC, larger the number of predictors included in the model, larger is AIC. While larger SSR indicate an underfitted model, larger number of predictors indicate an overfitted model. Therefore, AIC and BIC, by helping in identifying a model that has lowest AIC and or BIC values, find a balance between an underfit and an overfit model. AIC and BIC are very similar except for the last 2 components in the formulas. BIC penalizes the model when P is higher, that is especially when the number of predictors are higher. BIC strives for a simpler model as compared to AIC. The third information criteria statistic, Amelia's prediction criteria APC, is defined as APC equals the sample size n plus the number of predictors plus 1 denoted by P divided by n multiplied by n minus P multiplied by residual sum of squares SSR. By rearranging the above equation, we get some more insight into APC. APC equals SSR divided by n minus p plus p divided by n multiplied by SSR divided by n minus p, which equals variance of the residuals plus p divided by n multiplied by variance of the residuals, which can be rearranged as APC equals 1 plus p divided by n multiplied by variance of the residuals. So we can see that p and variance of the residuals play an important role in calculating the APC for a given sample size. Like in the case of AIC and BIC, the model whose APC is lowest is chosen among the candidate model. Lowest APC ensures lower SSR and or lower P, thus ensuring a balance between an underfit and an overfit model. Note, these information criteria statistics AIC, BIC or SBC and APC only help pick one model amongst the list of candidate models considered. Importantly, the statistics do not help in discovering or deriving a best model that is outside of the considered list of models. That brings us to the end of the lecture on predicted R-square, Mallows Cp, AIC, BIC or SBC and APC. See you back soon with next lectures on this topic on multiple linear regression models. Bye for now.